Sutherland has another book which has name of logical effort. You can follow that book also if you want to learn more things. And we also know that D, which is the stage delay, is equal to G times H plus P, all in small letters, like shows that it's a stage delay. This is D stands for delay, G is for logical effort, H for electrical effort, and P for parasitic delay. Parasitic delay is depending on following things, that how many number of inputs are there. So if it is one input NOT gate, the parasitic delay is 1. If it is 2 input NAND gate, parasitic delay is 2. If 3 input NOR gate, parasitic delay is 3. Note that all these numbers are normalized to with the time constant of a unit inverter. So this time constant depending on the various parameters of the particular technology. So we are not writing that. However, you have to read that in hidden, that its time constant is there, and the unit is right now unitless, but multiply with time it will become the seconds. Whereas if you look at the logical effort G, so we learn that if you are interested in finding out the logical effort, one input inverter is going to have 3 by 3. However, this is the fact that the ratio between NMOS and PMOS transistors are 2. If they are not 2, and if it is something else, this ratio will be changed. However, the ratio will be equal to 1. Okay. However, this ratio will impact other things like NAND gate, NOR gate. But if you are following the one book, which is just West and Harris, with the fact that the ratio between NMOS and PMOS are 2, then for NAND gate, it's equal to N plus 2 by 3, and this is equal to 2N plus 1 by 3, where N is the number of inputs. So if there are 2 inputs are there, then it's going to be equal to 4 by 3. If 2 input NOR gate is there, then it's 5 by 3. Similarly, like you can increase the number of inputs, like 4 inputs, then this will be 6 by 3 or equal to 2, and this is going to be equal to 9 by 3. I made mistake, right? So it's yeah, this was correct, right? So this is the logical effort, and H is the electrical effort, which is simply the ratio between output capacitance and input capacitor. Okay, so this is for stage, by the way. But if you are interested in different stages, which is creating a path, like in this case, there is a path you can see from point A to B, or point A to C, or maybe point A to D, all have some path. So in such cases, we are going to replace the small letter notations with the capital one, where F is nothing but GBH plus P. But we also learn that it's not only GBH, but it's going to be equal to raised to 1 by N times N. So that's the final equation for finding out the path delay. So this is the path delay. These are the number of stages. Just an example, you can see here from point A to B, there are 3 stages composed of NAND, NAND, and NOR. So those stages are defining that, and this N is also the same thing. Now G is the logical effort. Okay, but this is not the stage, but this is the path logical effort, which is multiplication of each stage logical effort. For B, it's a branch effort. which is equal to, so B is equal to multiplication of all such branches, where Bi is equal to nothing but C off path plus C on path divided by C on path. We'll use this, so then you will understand. And H is the total electrical effort, total path electrical effort, which does not look what is going inside, but you are interested in the final load divided by the input. So 45 divided by 8 is going to give the logical effort or the path effort 45 by 8. So it does not see what is inside. So let's use these equations and solve further questions. Here, the question is taken from West and Harris. I'm interested to find out the delay from path A to B given in the figure. Note that path A to B is this one, which is our like path of interest. You have to choose this transistor sizes to achieve this delay, and like this initial NAND 2, you can understand this is the notation for the 2-input NAND gate, right? And gate may present the load of 8. So it's lambda is actually the transistor width, but you forget about this for time being. Just understand that it's actually 8 is the input capacitance and 45 is the output capacitance. That is what it says. So we have to find out following things. We need to find out the delay, the entire part delay, as well as we need to find out what is value of X, what is value of Y. Notably, this X, Y, 8 are the drive. If you remember, we talked about that. There is a drive. Okay, we will use that again so that you will look at that equation also. Now, you can see here, if I want to find out the delay, it's nothing but GBH is to 1 by N plus P, and this is multiplied by N. So that equation we need to follow. For that, we need to find out, first of all, the simplest thing is H. H is actually C out, which is 45 divided by 8. So that's what you can write down over here, right? So you can keep it somewhere that H is available to us. Now I'm interested in finding out G, which is the logical effort, which is multiplication of all the logical effort in the path. So from path A to B, this gate number 1, gate number 2, and gate number 3 are coming on the path. Just to reduce confusion, I remove that number, but all these GIs has to be multiplied. So let's start from here. So I know that G1 for this particular gate, which is 2-input NAND gate, which has N plus 2 by 3. That's the logical effort, right? So this is 4 by 3. For the case of this one, it's a NAND gate, so it also follows same equation. So in that case, it's 5 by 3. If you look at this NOR gate, it follows the equation of 2n plus 1 by 3. So it's going to be equal to 5 by 3. So I know that G is nothing but 4 by 3 multiplied by 5 by 3 multiplied by 5 by 3. You can take all of them and you can write down accordingly, right? So now G is also available, H is also available, but we have to find out one more thing, which is known as B. That is a branch. So okay, so this is the thing which is given to us. So there are two branches I can see. One is over here and one is over here. I know that the branch equation is as follows, like the small b for one branch, it's equal to c off path plus c on path divided by c on path. So in that case, if I'm interested only in this first branch, I can write down that for the first branch there are 3x I can see which are on off path, whereas on path there is only 1x and divided by x. Sorry, I made a mistake here. It has to be 2x because on path only 1x is coming, off path 2x are coming, so this will become 3. Similarly, if you apply the same theory here, b2 is equal to nothing but on path is equal to y and off path again y. So y plus y divided by y, it's going to give you 2. So I know that b, which is multiplication of all such numbers, which are going to be equal to 2 multiplied by 3, that is 6. So you can have b is equal to 6. So you know all these numbers, you can keep that, and you can have something like, so multiplication of all these numbers are going to give you 125, right? So g times b times h is equal to 125. You can see here that we have 3 stages on path. So as per the equation which says that n times gbh raised to 1 by n plus p. Notably, p has left over here. So if I want to find out the p, I can see that this 2 input. So this is, first of all, this is the path going from here to here. So in this path, there is 2 input NAND gate is coming. So that's going to contribute p equal to 2. This is going to contribute p equal to 3 because it's a 3 input NAND gate, and this is going to contribute 2 because it's a 2 input NOR gate. Multiplication of all such numbers are going to give you p, which is this one. So 2 multiplied by 3 multiplied by 2, 12 is going to be your p. So when I'm keeping this, where n is equal to 3 multiplied by 125 raised to 1 by 3 plus 12, that will be your overall delay. So 3 multiplied by 5, 15 plus 12 is going to give me 27, right? So this is the total delay going from path point number A to point number B. But if you are interested in point number, let's say from A to B, if it is shifted here, or maybe here, let's call them A to C or A to D, then the answer will be different. Okay, let's assume that you might be interested in finding out the delay from path A to path D. Let's say this is D. So I'm interested in path A to D. So in that case, I know that G is equal to nothing but this is going to be 2 input NAND gate, which follows the equation of n plus 2 by 3, and NOR gate follows to n plus 1 by 3. That's the equation. So this is going to be equal to 4 by 3. This is going to be equal to, so let's call it G1, G2. This is going to be equal to 5 by 3. Yeah. And this is 2n plus 1 by 3. So this is going to be equal to again 5 by 3. So G3 is equal to 5 by 3. Notably, so all like G in this path is also same as what the previous path was. Okay, sorry, if I take this one, it's identical to what we are doing for D. So answer will be same. So what I suggest, let's have different path like this one. Let's assume that I am interested in path A to C, where output is maybe, let's say, 45. So in this case, again, this is going to give me 5 by 3. So G is equal to nothing but, capital G is nothing but 4 by 3 multiplied by 5 by 3. So it's 20 by 9. H is nothing but 45 by 8. And branch B, only one B is there. So you can write down that B is equal to B1 is equal to C of path is 2x divided by 2x plus 1x divided by 1x. It's going to give me 3. So GBH is going to give me 20 by 9, 45 by 8 multiplied by 3. And we need to find out that it's only 2 stages. So it becomes 1 by 2 multiplied by 2, that's delay, plus parasitics are going to be equal to 2 multiplied by 3, 6. So if you solve this, you can have the delay from point A to C. Similarly, you can find out from any point to any point the gate delay coming from the whole path. So this is possible. Now let's do some interesting thing over here, that I want to do the back calculation. I need to find out what are these x and y. I need to find out x and y. So in that case, if you look at from here, this y has h of, okay, these are x, this is 8, this is y, and this is also y. So I know that this is 45. I also know that f is equal to gh. If it is just one stage, I know that g for this one, for NOR gate, it's equal to 5 by 3. It's already known to me. This is 5 by 3 and this is 4 by 3. These are the different logical effort of each of the gate, and I am interested in this because that's on the path. And if I am looking for only this, f equal to g by h, that this is C out by C in, right? So in that case, C out by C in is going to be, this is going to be equal to 5 by 3 multiplied by C out is 45 and C in is nothing but y. So you can write down 5 by 3 times 45 divided by f, where f is nothing but 5 in this case, because okay, in this case it's 5. So you can find out y is nothing but 45 by 3, so 15, right, as expected over here. So you can replace these y with 15 because we found out from here, right? Similarly, you can find out other path, like in the case of x, where x is again can be found out with the fact that f equal to gh, where f already we found out it's equal to 5. By the way, it's coming with the fact that it's, if you remember, 125 raised to 1 by 3 we kept, where we kept it, okay, here, right? This is f actually, right? So I know that that path is going to give me 5, so that 5 I am keeping here. So in this case, g is nothing but, for I'm looking for this case, which is x. In that case, it's g2 is equal to 5 by 3, and h is nothing but c out. So if I'm looking at c out is nothing but total capacitance looking at the output of this particular gate, that's going to be equal to 15 plus 15, 30. Note that this number we found out from the previous calculation. And input capacitance of this gate is nothing but x. So in this case, you can find out x equal to 15 divided by 5 multiplied by 30, right? Now x equal to 5 by 3 multiplied by 30 by 5. So this makes 10. So in that case, this x will be replaced with 10 over here. Just for the sanity check, let's see if this is not given to us. If it is some value z, I know that it's 8, which was given in the already in the question. But what I'm saying, just to check whether it's matching what like with our calculation or not. So the stage that stage effort is equal to 5 g for this particular gate whose drive is z. It's going to be equal to 4 by 3 multiplied by c out, which is at this point I am having 3 NAND gates. So in parallel, it's going to make 30 divided by z. So if I take z one side, I'm going to have 4 multiplied by 30 divided by 5 multiplied 5. So this makes 8. So you can see that with even the back calculation, it matches the number with what has been given to you. But notably, this number has to be known because actually we need to know the 45 divided by 8, which is the electrical effort. If you don't know this one, then we cannot calculate any other things. So that has to be given, or you have to assume something. And that is what it has been presented over here, that it's 8 times the transistor width, and other things like lambda is the minimum number. That's what it has been kept here. But for the, we can say the simplicity, we can avoid it. Okay. So this was the question and this is the answer. Now let's go to the next question. This is, by the way, same question which we have like solved, where this was given 8, this was given y, and xx. Now what I want to do is I want to find out with the fact that if you look at the previous table which we have shown yesterday, that the effort delay is actually summation of all fi, where fi is nothing but gbh. So that has to be multiplied. So in that case, I am not solving completely, but you can see here it's already solved. So you can see here that the first part, first delay, it's g1 h1 plus p. So for this one, g1 h1, I know that g is equal to 4 by 3. H is nothing but I know that all these are 10. So 30 divided by 8, it's going to give me h, and plus 2 parasitic delay of this particular gate, it's going to give me the first delay. For the second one, d2, again gh plus p, where g is nothing but 5 by 3 multiplied by c out, here h equal to 15, x equal to 15. So at this node I am seeing 30 as output, and at the input side I am only seeing 10. Look at this, it's only one gate, it's not all 3 gates together. So at the input side I am going to see only 10 plus this is 3 input gate, so it's plus 3. So when you are solving this, different numbers are coming. Even for this one also you can write down, and you can see that adding all of them, 7 plus 8 plus 7, which is 22, which is exactly same number which we got it here. So any of the way you can follow and you can get the answer, right? But notably, in this particular technique, you should know that what is the input capacitance at each of the node. If you don't know what is y and what is x, you cannot have the final answer, because each stage needs the electrical effort. So that should be known to you. Notably, we also do not have idea that what is f without calculating the whole thing. Whereas in the previous technique, where you found out that f equal to 125 raised to 1 by 3, so that's actually quite easier to find out this x and y. Otherwise, it's not possible. So you can use any of the method, but this method is only possible when the drive is given to you. Drive is the one which is the input capacitance, right? So if it is not given, it's difficult. So in that case, you need to follow the previous equation, which is this one. D is equal to n times f raised to or I would say that GBH raised to 1 by n plus P, where P is multiplication of all such parasitic delays. This is multiplication of all logical effort, multiplication of all branch effort, and this is C out divided by C in, whereas BI is nothing but C off path plus C on path divided by C on path. Okay, so using that you can find out. Now the most important thing is here that, okay, before maybe going to this, I can give you one example. Let's assume that there is some gates are here like this. NAND gate is there, which has some capacitance. Let's assume that that capacitance is 10. Note that whenever I'm writing these numbers, it's actually in terms of some normalized to a capacitance, normalized to resistance, or normalized to some unit value. So right now it's with the unit capacitance. So if it is 10 and I'm saying that I have to connect something over here whose capacitance is 500. If you understand one fact that 10 is a small capacitance and 500 is a big capacitor. If you understand that if I'm going to connect this one over here, without connection, you might see something like this, 1 and 0. After connection, you might see something like this. So which was the need of the driver circuit, or it does not have enough logical effort. So in that case, you need to fix that. If you need to fix it, the best way is just add even number of stages of inverters. But if you are keeping these all equal, what I mean to all equal means if you are going to keep something like this, where this is 1 and this is 2, all will be cascaded by each other, then it says that this inverter can drive the load of 3, this inverter can also drive the load of 3, and this inverter can also drive the load of 3, and this inverter can also drive the load of 3, not the load of 500. So it has to be understood that we need stage of inverter, but you can see that with the stages I'm increasing the size of inverter such that the last one can drive the 500. But all these things has to be progressively, because if you are keeping again a bigger inverter over here, it cannot driven by the load of 10. You could have done it directly, but this is not possible. So you have to go progressively incremental. So in that case, what you need to do, I know that all of them are going to be equal to, so all of them, I know that they are the inverters. So many such inverters are there, depending on what is the C out, which has to be driven, and what is the input capacitance. So these two numbers are known to you. That C out by C in is known to you, right? Let's call that one as H, which is the electrical path, right? Notably, I'm keeping this H in capital, which signifies that I'm interested in the path delay rather than just one stage delay. If it is one stage delay, then it's a small h. Now, each one of the inverter is going to have the logical effort ratio of 1. So all this summation multiplication of all such GIs are going to be equal to 1. There is no branch. I can't say any branch. So branch is, you can say that it's not there. So that will not be coming into the calculation, right? And each one of them has parasitic delay of 1. Notably, when I want the parasitics, it's also going to be equal to 1. So when I'm going to write the whole equation, what is going to happen? That delay is nothing but n times GBH times 1 by n plus P. Now I know that I need to find out this n. This is not known to me. N has to be here. G is 1, B is 1, and H is equal to C out by C in. So this is effectively equal to C out by C in times 1 by n plus 1. So if you know what value of delay you want to achieve going from here to here, you know that, right? You know, with the fact that, let's assume that I'm telling you that you have to design a transmission line which is going from this point to this point. It's a wire. Here I'm feeding some, let's say, gigahertz of signal. I'm expecting here with, let's assume that there is some combinational logic. Here I want to have same 1 gigahertz, means 1 nanosecond is there, the clock period is. In that case, you need to make a budget that this is going to be equal to 0.5 nanosecond. So I am going to make the budget that the delay, rise time, so delay, rise time, even settling, all such time are much before 0.5 nanosecond. Let's make it 0.25 nanosecond. So you know that you can afford the delay of 0.25 nanosecond only. I made the budget, by the way. This is made by me as a designer. You can make another one also, like 0.35, 0.30, whatever you think that you can design it. Note that as you are shrinking this down, it's going to consume more power because switching is more. So it will consume more power, and power is depending on the fact that it's equal to CL times VDD square, right? If it is average power, if it is the dynamic power, which is equal to CL times VDD times F, the frequency of the operation. So accordingly, you are going to see such kind of things. In that case, you need to make a budget accordingly. So when you are making that budget, now you know what is the value of D. You have to normalize to the unit inverter, and then you can keep that over here. Like this D is also known to you. So you need to find out N. So this number of N is going to tell you that. So if this is 1, next one will be F, next one will be F square, next one will be F cube, and so on. I'm not going into this geometric progression series, but it's a big topic. If I'm going to tell you, like some of my MTech student has done just, you know, made the chain of inverters with equal size, with different size, and they found out this delay for different path. So that takes sometimes more time. So you just, I just suggest that you can either remember, or you can try to look at the solution which is given in maybe many books, or maybe on internet also. So these numbers will be 1, F, F square, and F cube. So if F equal to 2, then this is going to be equal to 1, 2, 4, 8, 16, and so on. When I'm writing 1, 2, 4, 8, 16, and so on, that means that first stage inverter, if I have designed with 1 and 2, next one will be equal to, if it is 2, it's 2 and 4. But note that just to make everything matching, what I'm going to do, if the first one is like this, like 1 micro divided by 220 nanometer, and if this 2 micro divided by 220 nanometer, I know that every time there is some multiplication number which is going on, and it's everything is uh, normalized with these numbers. So what I'm going to do, just I'm going to keep in this particular transistor m equal to 2 and m equal to 2 for the second stage. For the third stage, I'm again cascade this inverter, but I'm going to keep multiplier equal to 4, multiplier equal to 4. Again, so on, I'll go and I'll go till the last stage. All I'm going to connect. Note that here the unit transistor size from the last stage to first stage remains same, right? So that way you are increasing the width and you are giving the guarantee of having the matching. So this is the way to achieve uh, such a chain of inverter, and that is what this one is saying, that if you are designing a driver circuit, by the way, driver circuit is nothing but chain of inverters. Now just understand that driver circuit or buffer circuit, some analog engineers are saying voltage followers. Okay, this is for, but our popular name for digital engineer is driver circuit, which drive the load with the multiplication number of 1. So gain is 1. There is no change from here to here. The only thing is it can drive the bigger capacitance or the bigger load. So that is what this is saying, that if you have different driver circuit, one has only one inverter which is driving 64, like this is the capacitance value, and if you have 2, if you have 3, or if you have 4 stages, all have some different ratio is given to has been given over here. So you can see that here it's claiming that this particular configuration, which is driving from given value of incapacitance to the out, whose electrical effort is 64 by C in, can drive better way than the 4 stage. First stage is not capable enough, second stage is not capable enough, third stage is capable enough, fourth stage, if I'm adding one more inverter with the ratio of 23, that can also work, but the only thing is this will take more area, and you have to take care of speed. By the way, both of the things are interlinked with the fact that if you want to reduce if you want to increase speed, you need to increase width, because increasing width, it's going to decrease the resistance, at the same time it increase the capacitance also. So if you find out the trade-off value, you will see that you are landing up with increment in area to achieve the better speed. So everything is interlinked, and if you are adding some extra stages, it's going to cost you in terms of area. So you have to find out the optimum solution. So in that case, this shows that with 3 stages it's good enough for this one. But if you are adding the stages, maybe you can achieve the same speed, but you have to compromise on in terms of area, and of course in terms of power. As you have more width, of course the power will be more, because the current equation has, if I'm writing for just NMOS, muon Cox W by L, VGS minus VTH times VDS minus VDS square by 2. So you can see that as you are increasing W, most of the things are here constant. The only thing which is governing the current equation is W and L. L is also relatively constant because you don't touch that. It's going to be the minimum one. So width is going to control the current, and it's also control the power. As you are increasing the current, power will be increased. Power will increase, it will increase the speed, at the same time it's increase the area. So you need to find out the optimum solution. So that needs to be found out from the learned equation of the logical effort. Now let's understand following limitations of logical effort. The logical effort does not account for interconnects. When I'm saying interconnects, it's very easy term. Interconnect means one block of circuit is there and there is another block of circuit. If I am going to connect that, it's known as interconnect. Wire between two particular circuits, that's interconnect. The only problem is as you are increasing the wire, I know that if this is 1 and 2 and let's say some more wire is going from here, okay, and going to the 3 and 4. So let's say I made the routing, or routing is the wiring, if you remember, right? Routing is nothing but a wiring, and interconnect means the connection between two blocks. So this is a routing, but it's also interconnect because it's connected between two blocks. 4 and 5 and 1 and 2 has some interconnects. Now the thing is, you're working on some frequency 1 and 0, 1 and 0. Here also you are working with 1 and 0, 1 and 0. As you can see, there are two wires which are going from one end to another end. It can create the parasitic capacitance with the fact that it's epsilon A by D, right? So it's depending on this area and depending on the distance between two wires. So as this distance is big, it's not a problem, but as it's going nearby, you can observe that this signal can disturb this signal. So this signal is disturbing this signal and this signal is disturbing this signal. Such kind of phenomena is known as the crosstalk. So crosstalk will happen along with the parasitic capacitance. Along with that, you might be interested in sending the logic 0 and logic 1 as follows. But what will happen if it is a longer wire? During this wire, you might not have just capacitor, but you will have few more resistances also, which is known as the path resistance. And because of path resistance, in a path you will have IR drop. It's called IR drop, or the voltage drop will be there. Each one of the resistance will have some voltage drop. We are going to call that one as IR. R is the path resistance created by this path and multiplied by the current flowing through that particular interconnect. So path and all these things will happen. Along with that, sometimes it's not only the resistance and capacitance, but you will have something called inductor. Maybe in future I'll going to talk when inductor will come. It's not only the fact that it's going to happen at the low frequency, but even at the high frequency, inductor will happen because of the LDI by dt effect. I'm going to talk maybe sometimes later, but right now just assume that parasitic inductor will also come, capacitance will come, resistance will come, and as you are carrying a big wire, it's, look, let's assume that this is inside the chip, this blue boundary, it's inside the chip, and you are standing over here. You are full of the charge because you came from, like, you are in Mandi when it's like a winter season, you might be wearing some jacket or something where you are having the static electrical charge, right? When you are coming nearby and you are seeing such long wire inside IC, what it will do? It will dump these charges over here, and such things are known as the antenna effect. So all such things, whatever I talked till now, crosstalk, path resistance, path capacitance, path inductance, routing, all these things will not be accounted in the logical effort. But as a intelligent engineer, what you can do, you can find out these things from simulation and you keep that also for your calculation so that you can have the correct logical effort, but it's very difficult. So it's up to you how you are doing all this modeling part. However, even this is given that if you are interested in RC delay, you can read chapter number 6, which is also talking about what I told just now. And this is all these things happening because of the data path arrays, and lots of things are there which are going to be acting as an antenna, or it will have path resistance, it will also have the IR drop, it will also have the inductance. Next part is logical part effort. Explains how to design a critical path for maximum speed, but not how to design entire circuit for minimum area or power, as I told you, right? So this is not possible with this logical effort. Paths with non-uniform branching or reconvergent fan out are difficult to analyze by hand. So if it is uniform, till that time things are okay, fine, like this. But if somehow, like, if this is coming back here, or with some another logical effort like this, so if the memory circuits and other things will be there, the logical effort finding out through this technique may be difficult. However, you cannot say that it's not completely possible, but it's difficult. And the linear delay model fails to capture the effect of input slope. As I told you that if input is like this, you will observe different delay. And if the same thing, if your delay is like this, you will have different propagation delay, means rise time is changing. So that's also not accounted over here. So that has to be understood, that this slope has to be same, so that you can make the ratio as the same value. So these are the things for logical effort. Now there are some pitfalls and fallacies that defining gate delay for an unloaded gate. So do not do such things. Whenever you are designing something, always add some load. As I'm saying that, keep the CL of 1 picofarad, because we are going to watch that on oscilloscope. So that's input capacitance is around 1 picofarad. If it is more, you have to take more, so that you are accounting for what you are designing for. So if you are saying that, look, my NOT gate is working here, but when I'm connecting to some different circuits, it's not working, because it cannot drive it, because you have not accounted for the input capacitance of this particular circuit. So always keep the loaded gate. Second one is trying to increase speed by increasing the size of transistor in a path. Means if I want to increase the speed, means if I want to make it high speed, we have one experiment, we have done it on Simica. As we are increasing W, you can see that this speed is getting better and better. But that will be better till the time then when the capacitance offered by the gate is lesser than the capacitance at the output, means load capacitance is lower than the input capacitance. Till that time things are pretty fine, means electrical effort is greater than 1. Till that time things are fine. When it's getting lesser than 1, means Cin is getting dominating, then that's not the correct thing. Means increasing speed by increasing size of the transistor will be the wrong thing. Okay, so you have to make sure that what you are doing is known to you, what exactly things are going on with the output capacitance and the input capacitance. Third and the last one, trying to increase the speed by using a few stages. You might say that let's keep lesser stages, as we have learned over here. If I am keeping only one stage, so it will have a better speed. No, that's not true. As you are increasing the inverters, you might have the better speed, but increasing for longer chain, that's also not true. You have to stop somewhere by the logical effort equation, which is GBH raised to 1 by n, right? So all these things depends on fan in, fan out, and your required speed.